Come and explore electric circuits with me today. We're going to discover where electricity is made and how. We're going to investigate batteries, and we're going to have a look at how we can build electric circuits using conductors and insulators. For today's activities, we're going to make a simple electric circuit. So if you'd like to have a go, there's a couple of items that you might need to locate. We're going to need a couple of AA batteries. Going to be using some tape, so that'll be masking tape or electrical tape will be fine. Going to need some aluminium foil and a little light bulb. So this is a light bulb that I've taken out of a torch, so you may find a torch with a light bulb in like this, or perhaps a bike light, but do ask for permission before you take them. Electricity is used in our homes every single day, from switching on a light bulb to powering the television to using it to charge a battery in your phone. Electricity is created in a power station. Some power stations use fossil fuels like coal and oil and gas, and they get burnt to create steam. The steam then pushes a turbine around, and that generates electricity for us to use. But these fossil fuels are non-renewable. That means we're going to run out of them. So a lot of modern power stations now use renewable energy. And we can use things such as wind, solar power or hydroelectric power to create the same effect. All of these different things will push a turbine around and generate electricity. Electricity that we find in our homes is not the same as static electricity, although they do have electrons in common. With static electricity, the electrons build up on ourselves and that causes us to have a static shock. But with electrical current, the electrons are moving and they have a flow of electricity, and that's what makes it much more dangerous. So please resist any temptation to play around with electrical currents at home, and especially beware of sockets. Make sure you turn the switch off before you take a plug out of the socket. Sockets aren't the only place that we can find electricity in our homes. We often use batteries to power many items too. Batteries have stored electricity inside in the form of cells. So they have chemical cells where we've got two particular types of chemicals that will react with each other and generate an electrical current. Now, batteries have a positive terminal and a negative terminal, and that shows us the direction of the flow of electrons inside a circuit. The first battery was discovered by Alessandro Volta in the 1800s, and here's a simple setup that was similar to what he discovered. Batteries are essentially chemical reactions in little cells all neatly packed up together. And he discovered that if you use a particular liquid, and in this case we're using an apple, but you can use lemon juice or even salt water, and you put in two different types of electrodes, so these are actually just little bits of metal, so we've got copper and zinc here, it actually creates an electrical current. So we're going to use these electrodes and push it into our piece of fruit opposite one another. So the copper and the zinc, and you'll notice that these electrodes are zinced up to a clock, and our clock has now generated enough power to turn on. Batteries have all of this chemical energy stored inside, and the chemical reaction is called an oxidation reduction reaction, where one of the metals is oxidized and the other is reduced, and it creates an electrical current. When a battery goes flat, then it's finished doing as much of the reaction it can do as possible. But some of these reactions are reversible, which is why we have rechargeable batteries. Now, whether or not we use batteries or mains electricity, a circuit has to be complete. So let's explore circuits next. Here we have a few pieces of equipment that we can demonstrate an electrical circuit. We've got a battery, we've got a bulb, and we've got a switch and some leads. And these leads are wire, so we've got metal inside, which is our conductor, and the insulated plastic on the outside. So in order to make our light bulb switch on, we need to connect both ends of the battery to the light bulb, and they must be complete. If there's a break in the circuit, then the electricity cannot flow. So we're going to connect up one end of the wire from the battery to the light bulb, and I'm going to use another wire to connect the other side of the light bulb to the other side of the battery. And you can see that we've got our light turned on. The electricity is now flowing from the positive side of the battery through the wiring into the light bulb, back through this other wire and back to the battery. We've got a complete circuit. And the electrons are getting pushed as the current flows through. As soon as we introduce a break into the circuit, a light bulb goes out because there's now a gap where the electricity can't flow through. So here we have a switch. And with our switch, we can see that we've got 2 points we can connect the wires, but there's a gap in the middle. But as soon as we push this switch down, we can see that they're touching the metal parts in the middle there. So this switch we can add into our circuit so that we can turn it on and off when we like. So we're going to connect it in with another wire. And then as soon as we push down on the switch, our light bulb turns on. So this is how our light bulb switches are working at home. There's a break in the circuit, and as soon as we flick the switch, it closes that circuit up and it completes it so that a current can flow around. Now, if we wanted to light up more than one light bulb, we can add an extra light bulb into our circuit with a few more leads. But there's a couple of ways we can do this. We can just introduce the next light bulb to go next to the current one. So we're going to break the circuit from the switch and add it into that lamp. And then we're going to connect the two light bulbs up. And this is called a series circuit because the two light bulbs are one after the other in series. And as soon as we push our switch down, we can see that electricity is flowing, but it's lighting this one up, but not as brightly as it was earlier. And then there isn't any light coming out of this light bulb at all, which was lit up earlier. So that's interesting. What's happening is the electricity is flowing through the cables, but as it is, it's using up some of those electrons on this light bulb, and then there isn't enough electrons to make this light bulb switch on. The other way that we can connect the second light bulb up is in a parallel circuit. So let's disconnect our second light bulb and make our circuit closed again, back to our original simple circuit. Now we're back to our basic circuit. We can add the second bulb on in a different way. This is called a parallel circuit. We can add the light bulb onto the back of the first light bulb. So the second one is now joining on to the first light bulb. And as soon as we push the switch down, we can now see there's enough power there to turn both of the light bulbs on at the same time. So this is showing us that actually a different type of circuit allows the electricity to flow in a different way. And the electricity is flowing from the battery through the switch and to the first light bulb. And at the first light bulb, the electricity now splits. And it splits so that it can continue round to the other battery and can continue round to light up the other light bulb. And this is why a parallel circuit is really helpful for making our lights work in our homes. If we go back to our simple circuit, we can see our light will switch on the moment that we close that gap. Now, what do you think might happen if we were to turn the battery round? Let's have a look. So we're going to disconnect it, spin the battery round, and now our flow of electrons are going to go in the other direction. So in this case, with a light bulb, nothing is affected. It will still light up. But some things in our homes are affected by the flow of electrons. We're going to swap out our light bulb and substitute in a motor. And as soon as we connect that switch and complete the circuit, we can see the fan is spinning round at the end of the motor. Oh, nice and cool. Now, as we turn off the switch, the motor is going to run out of energy and it will slow down. But let's have a look what will happen if we switch the battery around. So I'm going to turn the battery around. So I'm going to disconnect the leads. We're going to turn the battery around and the electricity is now going to flow in the other direction. And as soon as we push the switch down, The direction of the fan has now changed, so the motor is going in the opposite way. This is all to do with the flow of those electrons. The electrons are getting pushed around the circuit, and as they get pushed around, they also change the direction of the motor. And that's because the motor involves a current flowing through a magnet. In 1821, Michael Faraday discovered that an electrical circuit can produce a magnetic field, and this in itself is what a basic motor is. Motors are in lots of household gadgets, from washing machines to lawn mowers to dishwashers to food processors. Lots of objects have a simple motor inside. So let's have a look at making one. We've got a battery and some very strong magnets called neodymium magnets, and some copper wiring. Now the neodymium magnets alone have a magnetic field, and because the battery have some metals inside that are magnetic, they'll stick together. But if we created a circuit from the positive end to the negative end of the battery using the magnets with our copper wire, then we can create a flow of electricity. And this flow of electricity creates a circuit and the motor will spin. So this is a basic magnetic field. So now we've got two magnetic fields. We've got the magnetic field from the magnets and the magnetic field being produced by the flow of electrons. Well, what do you think might happen if we turned our battery upside down? Let's have a look. So if we put the magnets at the top and turn it upside down, then our little dancer spins the other direction. And every time this little wire at the bottom goes near the magnets, that's completing the electrical circuit and allowing those electrons to flow. Now we've learnt about electrical circuits, let's see if you can have a go at home at creating your own circuit to make that light bulb light up. So we're going to need the batteries first, and we're going to add these batteries' power together. So one battery only has a certain amount of power, and if we put one on top of the other, we can combine that power together. So we're going to take a little bit of sticky tape. We can just put the two ends of the batteries together. So we want to make sure that one side is positive, the other side is negative, and that they're sticking together at the top there. Might need a little bit of assistance to stick those two together. So now we've got our battery where our power and our electricity is going to come from. Now we've got a light bulb, and we're going to have to connect the two together to create a circuit. So this is where our foil comes in. So we're just going to take a little bit of aluminium foil, and it's about 3 centimetres worth and the whole length of the roll. And we're just going to fold our foil over, just putting some creases in so that the thickness is increased. So the width of the foil is about anything up to a whole centimetre, or half to a whole centimetre. So now I've got a nice strip of foil here. What we can do is we can connect the one end of the battery to the light bulb, and we get the light bulb to connect to the other end of the battery to close the circuit and allow the electricity to flow. So I'm just going to fold up a few more folds at one end just to make it a little bit thicker, and I'm going to tape that to the bottom of the battery. So this is the negative terminal at the bottom of my battery pack, and then at the other end I'm going to be wrapping it around the light bulb. So on the light bulb here, we just want it to go around the edge. This is one of the reasons why we don't want it to be too thick, because we need to be able to touch the bit at the bottom there as well. So I'll pop a little bit of tape to keep it in place. There we go. So now we've got the negative end of our battery pack and the light bulb ready. And as soon as the two touch, our light bulb will come together. So this is a great way to see how a simple circuit can be created, and as soon as we put that break in, it breaks away. Now if you wanted to, you could create a switch. So instead of this being a complete wire, we're going to break our circuit. I can now stick our light bulb down at the top of the battery pack. Yes. And then as soon as the two wires, our foil connects together, we can create our circuit. So now we've made a switch. Now you can test out different materials this way too to find out what other materials are good insulators or good conductors. And if something conducts electricity, then the light bulb will come on, and if it's an insulator instead, then it won't flow through, the electricity won't flow through. So I'm going to try this bolt. So I'm going to wrap one end of the bolt with a bit of the foil at the bottom, and then I'm going to put this end to complete the circuit. So yes, we can see that that bolt is a very good conductor and allows the electricity to flow through. So you can try different objects out in your home, but just remember to disconnect your batteries at the end because they'll get rather warm like this. This electrical current happens as electrons get pushed through various different wires. They need a source to travel through. A lot of wiring that we see in our homes are made from metal, in particular copper. And copper is a really good conductor of electricity. That means it allows the electrons to flow through it easily. But you'll notice that lots of wires in your home are coated in plastic. Plastic is a really good material that can protect us from the electricity. We call it an insulator. It's not good at conducting electricity, so it doesn't allow the electrical current to flow through it. I have a special device here called an Otto, and this is a really interesting device to be able to test out different materials as to whether they are insulators or conductors. We're going to use some crocodile clips for this experiment. So I'm going to take a crocodile clip and I'm going to attach it to a different place on the circuit board, so each one has its own space. Now this Otto board is really interesting, and it makes sound, and it produces sound every time something is conductive and allowing the electricity to flow, and whether there's an increase in this conductivity. So for example, if I switch the board on, we can touch the end of the crocodile clip and we can hear a sound. And what's happening is it's sensing an increase in its ability to conduct electricity. And this is called capacitance. It's the same way that a touch screen works. Every time we touch the screen, it detects the fact that we have an increased capacitance. The ability to conduct electricity has increased. So what we can do is we can attach the other end of these leads to different objects. We know that all the crocodile leads are made of conductive material, so they can play a pretty cool tune. So I'm going to put a metal nut on the green one. I'm going to put a piece of wood on the red one. I'm going to put a screw on the yellow one, a key on the white one, and a penny on the black one. Now what we're going to look at is whether or not these objects can conduct electricity. And every time I touch one of these objects, if it makes a sound, then we know it's a good conductor. So let's try the penny, the key, the screw, the wood, ooh, and the nut. So the only one that doesn't conduct electricity is the wood. So if we take this off and replace it for something else, let's have a think about what else might conduct electricity. Now my mum always used to tell me that water and electricity don't mix. So maybe that's because it's conductive. Let's try it out. I've got a bowl of water here, so if I dangle one end of our red crocodile clip into the water, we can now see how well a conductor it is. So just by touching the surface of the water, we can see we can make it conduct electricity. So we can play our keyboard. So water conducts electricity. That's really interesting. I wonder, I've got some fruit over here that contains water. I wonder if it will work. Let's give it a go. If we take off a couple of objects, we can attach the leads to a apple and to a old looking banana. Maybe these will play the notes too. Let's give it a go. We can play some music with fruit and water. Who knew? Here's another way that we can demonstrate that water conducts electricity. So our bodies are actually made of water, and we're going to use our bodies in this experiment with a special toy. So this is a special toy called an energy stick, and at the bottom we've got a battery that's connected to a buzzer to make some noise and lights to light up. But we'll see from this side there's a little bit of metal on either end, but they're not connected. So we have to create that connection and close the circuit using our bodies. So if I hold on to this end of the energy stick and then this one, we close the circuit and it lights up. So our bodies are conducting the electricity, allowing the electrons to flow through and creating this sound and light. If I had some volunteers here, we could actually connect this electrical circuit from one end to the other using our bodies. So if everybody stood in a circle holding hands with the start of the circle this end and the end of the circle that end, then we could allow the electrical current to flow through and create this effect. But instead of using other humans, I have some water. So we're going to take the water and we're going to put the energy stick into the water here. I'm going to hold this end of the stick and connect the circuit by touching the water. And again, you can see that water is conducting the electricity. A pretty cool experiment. Water's not the only liquid that can conduct electricity. In fact, lots of other liquids are used in an experiment called electrolysis. So we're going to demonstrate this electrolysis here and show how electricity can flow through one liquid and create a chemical reaction. So for this experiment, I have this liquid here, which is called copper sulfate solution. I'm going to use a battery and we're going to connect it up with some leads. I'm going to take two types of metals. I've got a zinc washer and I've got a copper penny. Now we're going to do an extra step with this experiment. So rather than it just being electrolysis, we're going to add in a little feature. I'm going to write my name on the zinc washer. So I'm going to put NitroJen nice and clearly on here. Okay. There we go, NitroJen. And we're going to take our zinc washer and our copper penny and attach them to different ends of the battery. And what we're going to aim for here is to get the copper to come off of the penny, travel through the liquid and deposit itself on top of the zinc washer. So we have to think about the flow of electrons. So we're going to need to make sure that our copper gets attached to the positive side of the battery and the zinc washer gets attached to the negative side of the battery. We're going to dangle them in the liquids and allow the electrical current to flow. So I'm going to hold it here for a couple of minutes and we'll have a look what happens. So that's been about 2 minutes and we can see that the copper has started to build up on the zinc washer there. So as the electricity has been flowing from the positive terminal through the wire to the copper coin here, the copper ions have been allowed to pass through the liquid because this is copper sulfate, so it allows the ions to freely flow, and they've been depositing on this zinc. Now, if I just disconnect the battery, the reason that I put a name on here with some ink is because the ink can protect the zinc from being coated in the copper. So if I then wash off the ink, we should reveal the zinc underneath. So here I have a little bit of acetone. So this is the same liquid that we'd use to get rid of nail polish. It's just going to dissolve the ink that was on the zinc washer there, and then we'll be able to see the zinc coming through where it's been protected from the copper depositing. Okay. Now if I just block that off. Okay. So here we can see that the ink has protected the zinc from the copper being deposited. And if we leave it a little bit longer, we'll get much more of a copper colouring. Now this is really interesting, and electrolysis like this gets used in a method called electroplating. And in fact, this copper coin gets electroplated. So in the olden days, our coins used to be pure copper, but nowadays, to make it cheaper, because copper is quite an expensive metal, we take a cheaper material and it gets plated in the more expensive one. So underneath here we have a cheaper metal and the copper is applied on top. And the same process applies with jewellery making. So gold and silver are expensive materials, so quite often they are plated, so using a cheaper metal and then coating it in gold and silver.